A 0.05 kilogram ingot of a metal is heated to 20 degrees Celsius and then drop into a beaker containing 0.400 kilogram of water, initially at 20. If the final equilibrium temperature of the mixed system is 22.4, find the specific heat capacity of the metal. Okay, so the whole thing is about the principle of calorimetry, that when two bodies are in thermal equilibrium and they exist in an isolated system, the energy transfer from one body is equal to the energy transfer to the other body from the water or body at a higher temperature to the body at a lower temperature until thermal equilibrium is obtained or achieved. So the ingot, which is the metal, is initially at 200 degrees Celsius. So from the law of conservation of energy, or from conservation of energy, heat hot body transferred must be equal to cold body. The ingot is at a higher temperature, and Q, this is M of the ingot, specific heat capacity of the ingot times the change in temperature, delta T, which is also equal to mass of the water, C of the water, times delta T. The mass of the ingot, 0.05. Specific heat capacity, that is what we are looking for. The change in temperature, the initial temperature of the ingot, 200. So 200 minus temperature at equilibrium, which is 22.4. This is equal to the mass of the water, 0.4. Then specific heat capacity of water, 4,200 times the change in temperature. The water, the final temperature of the mixture is always greater than the initial temperature of the water because the water would gain. So 22.4 minus 20. So C is what you are looking for. So simple of a question. So now this is 200 minus 22.4. 177 what? Charlotte, you are not here. Adjoa and Co. Confirm the calculation for me. Then 22.4 minus 20. This is times 2.4. Multiply this by this for me. 0.05 times 177.6. Equia Watima and Co. Do it for me. Please, let's not waste time when it comes to these things, okay?
6.88.
2.88.
8.88.
8.88 C is equal to, what is this product to?
Yeah, 4,032.
4,032. Therefore, C is equal to 4,032 divided by 8.88. And this is equal to at 4 what? Come again.
454.
454 joules per kilogram per Kelvin. Okay. So this will be the specific heat capacity of the metal ingot. Now the second question is that the second question says that what is the amount of heat energy transferred to the water as the ingot cools? Because the ingot is at a higher temperature and it is given out to the water, cold water, the amount of heat energy that is transferred must be equal to the total energy transferred by the ingot, which is its mass 0.05 by its specific heat capacity, which is this 454 times the change in temperature 177.6. And this approximately must be approximately 4020. So that's it. Then the big question. A cowboy fires a silver bullet with a mass of hello.
Please, when the answer I have is 4030.
Yes, in your case, I saw that there was slight difference in this one. You had 457 or so. Check.
I had 454.05. 4.05.
I saw a slight change in one of your calculations, the reason for which you had this answer. So go through this thing, you see it. Let's quickly tackle the second question. A cowboy fires a silver bullet, with a mass of 2.00 gram with a muzzle speed of 200 meters per second into the pine wall of a saloon. Just into a wall. Assume that all the internal energy generated by the impact remains with the bullet. What is the temperature change of the bullet? Here, some of you were confused with relating the velocity of the bullet to change in temperature. But the thing is, if you fire a bullet, what the kinetic energy the bullet actually moves with or obtained by the bullet is as a result of the elastic potential energy of the spring. That is why in firing a bullet or gun, you have to pull back, I've forgotten the word used in describing that, but you have to click a metal something back. When you do that, it's like pressing or compressing a spring. Then the moment you release it, okay, the elastic potential energy of the spring is converted to the kinetic energy of the bullet. Okay, so here elastic potential energy is equal to kinetic energy. In the same situation, the kinetic energy of the bullet upon impact, when the bullet impacts with the pine wall, is converted to heat energy. Is that okay? So, how mv squared must be equal to the internal energy after impact. So, mc delta t. The same masses. So, m and m will cancel out. So square of the velocity. So delta T will simply be equal to V squared over 2C. What is the velocity given? The velocity given to the bullet.
200 meters per second.
So 200 meters per second squared over 2 times the specific heat capacity of silver, which is given as 234.
234.
So the change in temperature will be equal to, yes, what's the change in temperature?
The change in temperature will be equal to
200 squared divided by this. Please, let's see.
5.47 Kelvin.
Come again.
85.47 Kelvin.
That's all. That is all. Then the B question, suppose the cowboy runs out of silver bullet and fires a lead bullet of the same mass at the same speed into the wall. What is the temperature change of the bullet? Okay, so here the only difference is that we have same conditions, same speed, but we are using lead bullet instead of silver. So the only difference would be the specific heat capacity. So 200 squared divided by 2 times the specific heat capacity of lead, 128. So that would make the difference. And what is that? Calculate delta T in this case for me.
156.25 Kelvin.
156.3
25.
Kelvin. So simple of a question. Not difficult at all. But if you don't take care, you may think, oh, it's a loaded question. Miss Lydia is torturing us and so forth. All right, please, any question? Any question? All right, so let's finish up on our calorimetry. So as seen yesterday, we've even been applying the principle of calorimetry in our problem solving. Okay, just now the question we just solved, we applied the principle of calorimetry, which is this. So the principle of calorimetry is actually the physics of heat measurement, or it's about measurement of heat using a gadget, a special gadget known as the calorimeter. Okay, so calorimetry is the principle, whereas calorimeter is the gadget. The calorimeter, so yesterday I gave you the principle. The principle actually says that when two bodies in thermal contact, okay, are in isolated system, okay, heat energy can always be transferred from the body at a higher temperature to the body at a lower temperature, okay, until thermal equilibrium is obtained, meaning that heat transfer is always from a body at a higher temperature to a body at a lower temperature. And the transfer would cease when the two bodies have attained the same temperature. Okay, provided the system is an isolated one An isolated system means that it's a kind of system whereby no heat energy can move from the system to the surrounding or from the surrounding to the system. So if you have something like that, then heat energy can be transferred till the two have attained the same temperature. Now the calorimeter is like the vacuum flask. You learned about the vacuum flask. The vacuum flask is used to preserve temperature of foods. So if you want your food to remain cold or warm for some time, you put it in a vacuum flask. The vacuum flask also has some interventions which tries to or helps it to maintain the temperature for quite some time. And you learned about this in JHS. Okay. The calorimeter is also similar. It's just like this. It's a metallic vessel. A metallic vessel. Then with a lid. Now within the metallic vessel, there's another one, which is actually the system itself. This one has a lid. So it is usually covered. Then there is an opening within the lid where thermometer, this laboratory thermometer, can be inserted into it. Now, to enable this to maintain or to help it work as an isolated or closed system, there is a lagging effect between the calorimeter itself and then the vessel. So there is a lagging effect. This is a lagging effect. The lagging effect can be fiber, coconut fiber, or can even be styrofoam, something which would the lagging effect is actually a non-conducting material. It is sandwiched between the metal vessel and the calorimeter within, so that they don't establish direct contact. Okay, now the surface of the calorimeter and then the metal vessel. This is the metal vessel, and then this is the calorimeter itself. There is this lagging effect both around so that they don't establish contact, direct contact. This is a thermometer. Now, substances whose specific heat capacity and all that is put into this. So, assuming we want to determine the specific heat capacity of liquids, it is put into the calorimeter here. Sometimes with a stirrer. So there is a stirrer here. Stirrer. This is how the calorimeter looks like. Okay. Now we can use the principle of calorimetry to determine One, the principle of calorimetry can be used to one, determine the specific heat capacity. Heat capacity of liquids. And by determining the specific heat capacity of liquids, it means we can use this principle to identify liquids. To identify liquids. Because if I go through the process and I'm able to determine the specific heat capacity of a particular liquid, and it's 4,200 joules per kilogram per Kelvin. Clearly, it tells me that the liquid is water. So by knowing the specific heat capacity of liquids, it means you can use this principle to identify liquids. Then we can also use this to determine the temperature of very hot sources. Sources of heat. If we have a very hot source and the place is the temperature is such that we cannot go close, we can also use this principle of calorimetry to determine the temperature of the very hot source. Very, very hot source of water, such as furnace, oven, and all that. Then we can also use this to determine specific heat capacity of solids. So in as much as we can use it to determine specific heat capacity of liquids, we can also use the method or the principle to determine the specific heat capacity of solids. So these are some applications of the principle of calorimetry. Now let's go through it and see how we can use this principle of calorimetry. There are two methods. Can I clean the board? Can I?
Yes.
Okay. So in using the principle to determine the specific heat capacity of liquids, there are two methods. One, the first method is using the method of mixture. Two methods of so one, the method of mixture. The method of mixture. And then two, the electrical method. We have the electrical method. We'll quickly go through these two. Now, in the method of mixture, maybe you want to determine the specific heat capacity of liquids. So what we do is that a metal is heated to a particular temperature. So let's take this to be the metal that is being heated. This is a thread connecting to the metal, so that if we are ready to transfer, we do so. We have a source of fire here. So a metal is heated to some temperature. Let's say temperature of the metal 100. We heat it to 100 degrees Celsius. And then quickly transfer. When the metal is heated to that temperature, we quickly transfer this into the calorimeter. So with the thermometer inserted and then the vessel, the stirrer. So the metal, after it's being heated, is transferred into the calorimeter. There's the metal. Then it is stirred. So the stirrer inserted within the calorimeter is pushed up and down for some time. Okay, and the reason is that when you are stirring the whole mixture, what you are doing is that you are ensuring an evenly distribution of the heat energy. Okay, you are ensuring the even. So, but before you do that, what you do is that you determine the initial temperature of the mixture. So let's assume the initial temperature, let M MM MW MC. MM stands for the mass of the metal. Mass of metal. MW, mass of water. MC, mass of calorimeter. Then CM, CW, CC. This represents specific heat capacity. Capacity of metal. Now, CW of water. CC. This is of calorimeter. We are saying that let the initial temperature of water be T1. So T1, initial temperature of mixture, of the mixture. Then T2, final temperature of mixture. As for T, we are saying that let T, capital T, represent temperature of the metal. Temperature of metal. So this are our data. Please take note of them. This is our data. M, MM, MW, MC, CM. Okay. Now, as for CW, let's indicate that as CX instead, because that is the unknown liquid we want to identify. We want to use the method of mixture to determine the specific heat capacity of an unknown liquid. Okay, because we understand that knowing the liquid, Amma.
Sir, please end first.
Amma, I can't hear you.
Please end first.
Okay,
Maybe
so what
you
I'm
might.
saying is that let Cx represent the specific heat capacity of the unknown liquid. Okay, let's not make it as water, unknown liquid, because that is what we want to find. Go ahead with your question, Amma.
Sir, please, you've answered.
All right. So let's apply our law of principle of calorimetry. Now, through conservation of energy, energy transferred by the hot metal is equal to the heat energy by the cold. This is the liquid heat energy gained by the liquid plus the heat energy gained by the calorimeter. This wouldn't be only the water, because you see, when you put hot water in a glass or even a plastic cup, okay, the water within whatever is within the glass or the plastic cup will be heated. Then you also realize that the glass or the plastic cup would also be heated. So both, whatever is within the container and then the container itself will be heated. And here the unknown liquid is within the calorimeter. So heat loss by the metal will be equal to heat gained by the liquid plus the heat gained by the container. And the container is the calorimeter. Please, is that understood? Class, is it understood? Give me feedback.
Yes.
All right, so let's identify the heat loss by the metal. This is heat loss and then gain by the two. The heat loss would be equal to the mass of the metal, mm, times the specific heat capacity of the metal. Charlotte.
Mr. Dia, please, can you turn off your light? Because I can't see the board well.
Hey, if I turn the light, anyway, let me turn it off so you see it for yourself. Can you still see?
Yes, please, it's better.
Class, is it better?
I don't know for the others. Then.
Class, is it better?
Yeah, it's okay.
Okay.
Sir, please, it's fine.
Okay. Charlotte, 1 minute. Okay, so mass of metal times specific heat capacity of metal times the change in temperature. The change in temperature is the initial temperature of this, okay, temperature of the metal, which is capital T, minus temperature at equilibrium, the final temperature of the mixture, which is T2. So this will be the heat loss by the metal. Then let's look at the heat gain. Q gain. The Q gain will be equal to mass of the liquid the specific heat capacity of the liquid, which we don't know. I want somebody to help me determine the change in temperature here. What do you think will be the change in temperature for the liquid? Yes. What will be the change in temperature? Amma, Kelvin. Amma, what is the change in temperature?
Mr. please, you didn't give any letter representing M for liquid.
Pardon?
You didn't give any letter to represent the temperature of the liquid.
Then who told you? I said let the initial temperature, okay, initial temperature of the mixture be T1. And let the final temperature of the mixture be T2. Okay, let me take it up. Time isn't on my side. So it will be the final temperature of the mixture minus the initial temperature of the liquid, which is T1. Then the heat gain by the calorimeter, Q by cal, would also be mass of calorimeter, specific heat capacity of the calorimeter, times the same change in temperature, T2 minus T1. So both would have the same change in temperature. Both the liquid and then the calorimeter would have the same change in temperature. Please, is that understood? Therefore, when we equate the two equations, we have MM, CM, T minus T2 is equal to ML, CX, T2 minus T1 plus MC, CC times another T2 minus T1. Okay, now what we are interested in is determining the specific heat capacity of the unknown liquid. So we make Cx the subject. Therefore, Cx will be equal to this. Cx is here. We must send the heat gained by the calorimeter to the other side of the equation. So we have MM, Cm, T minus T2 minus MC, T2 minus T1 all over mass of the liquid times T2 minus T1. So this is how we can use the principle of calorimetry to determine the specific heat capacity of an unknown liquid, Dx. Is there any question? This is using the method of mixture? Please, is there any question?
No, please.
Now, if it's about
No, come on.
Lizzie, mute yourself, Lizzie. If it's about using this method to find the specific heat capacity of a metal, all that you do is that you make the metal, whatever you are looking for, the subject. Establish the equation, okay? Heat lost by the body at a higher temperature must be equal to the heat gained by maybe the liquid plus its container. Then make whatever you are looking for the subject, and you are good to go. Okay. Now, what about, please, if you are writing, quickly do this, and then I need to clean the board to continue.
Mr. Dear,
Hello, Charlotte.
please, your video is paused on my screen.
Please, is it a global problem? Class, is it a general problem?
No, please.
And then, Charlotte, can you rejoin?
Yes, please.
It
Please
must
don't
be,
clean the board.
Amma.
Sir, please, when you say mixture, are you not saying the metal plus the liquid,
Yeah,
or it's
exactly.
just the liquid?
Exactly. Okay. Whatever is within the is put within the calorimeter is the mixture. Okay.
So, sir, the T1 is not only the liquid's temperature, but the metal's temperature as well.
Amma, this is
Is
what
that
I
right?
said. I said let T1 represent the initial temperature of the mixture. So the initial temperature of the mixture here, I'm referring to the water and then the calorimeter, because the metal is not immersed into it here. Is that okay?
Yes.
When the metal is transferred and it is stirred for some time, it will give us the temperature, the final temperature at equilibrium. And that is what is indicated as T2. Are you okay?
Yes.
The initial temperature T1 means that when I pour ice water in a cup, the temperature of the cup and then the ice water will be the same. That is how come the change in temperature for the liquid and then the calorimeter is the same. T2 minus T1 here.
Okay, sir. Thank you.
All right. Now let's look at using this to determine a very hot source, okay, of fire. Maybe the temperature of the source is so high that it cannot be accessible to people. Maybe you want to measure the temperature of a source, but the temperature is also too high to the extent that we can't go close. In that case, we can use the principle of calorimetry to determine it. And this is how we do it. Let's assume this is the very hot source. This diagram. This time, the source is so high that the temperature of the source is so high to the extent that we can't go close. So we indicate the temperature of the source to be Tx. So usually we place a metal on a very long handle and then put it into the fire. example, an oven. We don't want to go close to the oven, so we put a metal, okay, on a handle, and then direct it, put it into the oven. Make sure that it is heated for some time. Okay. So when it is so much heated for some time, what we do is that we quickly transfer it into a calorimeter containing some water or any other liquid. Then we stir for some time. Okay. We stir for some time and then establish energy conservatory equation, just as we've done. So this time around, the equation will be mass of the metal, specific heat capacity of the metal, times the change in temperature. The change in temperature is that Tx, which is the temperature of the source, which we don't know, minus temperature at equilibrium, final temperature at equilibrium, to be equal to mass of water, specific heat capacity of water, times the change in temperature, Tf minus T1. Then that of the calorimeter, the container. Then the same Tf minus T1. This time, we are only interested in this, Tx, because that is what is unknown to us. So we try and then make Tx the subject. So Tx minus Tf is equal to MWCW Tf minus T1 MC CC Tf minus T1, all divided by MM CM. Then we eliminate Tx. Okay. Or we eliminate Tf rather. This will be equal to Tf plus the whole of this. All divided by, no, this, just this. This divided by. So by establishing an equation and making Tx the subject, you determine or you are able to obtain the temperature of the source, which you didn't know, which the value is so high or the magnitude is so high that you wouldn't want to go close. By establishing this equation, you can be able to. Now this temperature Tx will be a little bit less than the ideal or the real situation, the real temperature. What we are getting as Tx, which by our view represent the temperature of the source, will be a little bit less than the real situation. Why do you think so? Class, why do you think the value of the unknown temperature would not be exactly as how it's supposed to be? Yes, can I get your views as to why Tx will be a little bit less than the real situation or the real magnitude of the temperature? Can anybody try? As many? Victoria, can you try?
I feel like because the fact that like it's like an approximation of what is on the ground. So the real situation, like the temperature can be lost to the environment. So like it would like be lesser than that or something.
So as when you said, it is the shortage is due to, it's
It's
actually
actually
due
due.
to
I'm coming.
I'm taking a
I'm
shot.
taking a shot.
So you
So
answered
you
it,
answered it.
but then let me know the reason for the drop. He said there will be a drop because it's an approximation. What actually accounts for the drop? That's what I want to understand. Victoria, are you there?
Jesus. Yes, please.
So
But
in
please,
your view, what actually accounts for the drop?
I don't have any idea about that one.
Okay, more views. What do you think would account for the drop? We are saying that TX will not be original as the source. What do you think accounts for the loss in energy or the drop in energy as, oh, Kelvin, Festus, and Co. Try. Okay, Victoria, you said it unknowingly. You see, this is because the source is so hot that we can't go close. So what we are doing is that we want to use something, put the metal into the source or in the source, and then when it is heated for some time, we transfer from the source to the calorimeter. Now, what will happen is that during the transfer of the metal from the source to the calorimeter, there will be loss of heat energy as a result of the transfer. Okay, it is not direct. It is not just like from here to here. No, we are using something to take it from a distance to the current situation. So during the transfer, some heat energy will be lost to the surrounding. And that is what will account for the drop in energy. Okay, the drop in, temperature rather from the source. All right. Now let's look at using the electrical method. We've gone through using the method of mixture. What about the electrical method? With the electrical method, we still have our calorimeter. Charlotte, are you there? Or she wasn't able to join again? Adwa? Adwa? Ekwe Abwatima? Okay, you are here. So, using the electrical method, a heater is inserted within the calorimeter. We have an immersion heater. Then an ammeter is connected to the same circuit. Then source of EMF. This time, all that we are doing is that we want to heat this using electrical method. Then a voltmeter is also connected in parallel to the source of EMF. We still have a calorimeter as this. Well lagged so that there's no heat, or we minimize heat loss. Well lagged calorimeter. So this is an immersion heater, the heater we use in our homes. This is still the heater we use in our homes. So maybe the liquid whose specific heat capacity is to be determined is here. Okay, this is the method of using the electrical method. Now, before switching on the meter, of course, we need to know the mass of the liquid, the initial temperature T1, then the final temperature T final. Okay, so this represents mass of liquid. Initial temperature of liquid. Let's also have, okay, this is final temperature. Then CW or CL and CX represent heat capacity of water. Then CX is the unknown heat capacity of liquid. That's what we are looking for. So we have determined initial temperature of the liquid. Okay. So what is done is this. The key is closed so that current flows. All that we want to do is that we want the heater to be doing the heating before we're using a body being heated from one end and then transferring it to to the calorimeter. This time around, we want to do the heating using electricity. Okay, Amma.
Sir, please, you writing water doesn't mean the liquid in the calorimeter is not only the liquid but as well as water.
No, what I'm saying is that, oh, Amma, thank you. I think I'm writing liquid and water at the same time. Thank you. So, let's use liquid instead because that is what we are looking for. Thanks for the attention. So it means the water then will not be there. Okay, it's just liquid whose specific heat capacity is to be determined. So we want to do the heating using electrical method. So we switch it on, and then the heater heats up the liquid in the calorimeter for some time. We decide a time, or you can heat it to maybe a certain temperature, 100 degrees Celsius or whatever. Whichever temperature we heat it up to becomes our final temperature, TF. Then we establish the equation heat loss is equal to heat gain by liquid plus calorimeter. Okay. Now, electrical energy E, let me write it in words first. Electrical energy is equal to the product of power and the time taken and time. The heat loss is, this heat supplied by this is by electrical energy, is the electrical energy that is converted to the heat energy. So the heat loss is equal to the electrical energy. So heat loss is equal to power times time. Now power is also equal to current times voltage. So we can break this down to I V T to be the heat loss. And this is the reason why, you see, the circuit has an ammeter to read. Ammeter reads current. The circuit has a voltmeter. Voltmeter reads voltage drop or potential difference. Okay, as for the timing, we decide when to start heating and when to stop it. So it can always be determined. So when you relate, we have I V T being equal to M, mass of the liquid, specific heat capacity of the liquid, which is not known or which is to be determined, times the change in temperature, T final minus T1. This plus mass of the calorimeter, specific heat capacity of the calorimeter times T final minus T1. Okay, therefore Cx in this case is equal to IVT minus MC CC TF minus T1, all divided by ML times TF minus T1. So simple. Class, I hope it is well understood. Class, I hope it is well understood. So the difference is just that this time we are using electrical method to do the heating, not heating a metal and transferring, but using an immersion heater to do the heating. Okay. The electrical energy can be expressed in different ways. One way is what I said earlier. E is equal to P times T, which is the power times time. And power in itself is also equal to current times voltage times time. So the electrical energy can be this this. We can also express the same electrical energy differently because voltage, electrical voltage, is given by current times resistance. We can also break this down to, when we substitute IR in place of V, we have I times IRT, giving us I squared RT. So the electrical energy can also be expressed as such. Another way of doing the same thing is that, you see, from Ohm's law, the Ohm's law equation, current is equal to voltage over resistance. So we can also substitute V on R in place of this I. So we have V squared T all on R. Okay, so these are different ways we can express electrical energy, and depends on how the question or whatever information is given in a question. Okay, so as usual, we'll be solving similar examples just to, be armed with what and what to use based on information given. Please, if you have any question, you can ask. Is there any question? Okay. Now we can also use the same electrical method to determine the specific heat capacity of metals, maybe solid metals. And that wouldn't need the calorimeter. But what we'll do is that, because the metal is a solid one, we create a hole. This is the metal. This is the metal. We create a hole within the metal so that we can insert the heater. So this is a solid block of metal whose specific heat capacity is to be determined. Then we create a hole. We drill a hole within so that we can insert an immersion heater. Okay, so then the whole circuit is on, switched on for some time. Don't forget, this time it's a solid metal. We are not using any liquid and all that, or calorimeter. So this is a solid block of metal. Amma,
Sir, please, the coils, which metal was used to make it?
oh, it's a heater. Immersion heaters are nickel, so it can be nickel or platinum. So you leave that for us. We'll give you the details of whatever. Okay, it's just an immersion heater, the meter we use in our homes.
Okay.
So T1 is the initial temperature of metal block. Then here we can also use a thermometer to determine the final temperature. So let the final temperature be T2. So we can insert a thermometer within the hole to record the final temperature. So thermometer. So the same principle, heat supplied by the heater or the immersion heater is equal to the heat gained by the block. Okay, so heat supplied by immersion heater equals heat gained by metal block. And so you establish your equation. Heat supplied by metal block can be, heat supplied by heater can be power times time. Then the heat gained by the metal block, sensible heat. This is sensible heat. M, mass of metal, Cx, which is not known. Then T2 minus T1. Therefore, Cx is equal to P times or Pt over M of metal T2 minus T1. Or this is also equal to power is current times voltage. So IVT over MM T2 minus T1. Or V squared, let me make it I squared RT over MM T2 minus T1. So it depends on whichever information a question gives you. Okay. So this is it with the method, the electrical method of determining specific heat capacity of material. Please, any question? All right. I'll send a question to that effect so that you try your hands on. Let's quickly move on to change of state or change of phase. Change of state or phase. We've discussed change of state for some time when we started heat. So substances exist. For now, we know that substances exist in 3 states: solid, liquid, and gaseous. Okay. Now, before solid changes states to liquid, what must happen? Yes. Before solid changes to liquid, what must happen? For a solid to change to liquid, what must happen?
Heat must be applied to it.
So heat must be applied to it. So technically, what you are saying is that the solid must absorb heat. Okay. Now, when the solid absorbs heat energy, what will happen before its state will change? When the solid absorbs heat, what happens? Can you take us through what and what must happen for its state to change?
When it absorbs the heat, it starts to lose or release the cold it had, and the coldness is what was keeping the liquid in a solid form. So as it loses that low temperature, it feels
Mhm. Professor Egua,
weak.
Egua is confusing Mr. Edria. Okay, Oheneba, can you share your opinion with us for a solid to change to heat? Sorry, liquid. For a solid to change to liquid, what? Mhm,
So for solid to change to liquid, I
mhm.
know a heat must be applied.
Yes.
That's all I know. Heat must be applied
Okay.
for it to change.
All right. So, as you all said, the substance must absorb heat energy. Okay. So, changing from the solid state to liquid state of any substance has to do with absorption of heat. And the reason why the body must absorb heat is that, you see, in solids, the intermolecular bonds is greater, okay, or stronger. There are stronger intermolecular bonds in solids. If you want to separate the molecules so that they become a little bit free as it pertains in liquids, then you must break the stronger bonds. You must break the stronger bonds. And the breaking of these stronger bonds is as a result of absorbing energy within the body. Is that okay? So when the substance absorbs energy to a particular temperature, which we call as the melting point. The melting point. So change of state occurs at a particular temperature. And this particular temperature at which change of state occurs is a melting point or freezing point or boiling point. So every change of state occurs at a particular temperature. And that temperature is either the boiling point, melting point, freezing point of the material. Now, when we get to that temperature, every amount of external heat energy introduced into the material increases the potential energy of the molecules. Okay, increases the potential energy of the molecules. It does not increase the kinetic energy. So when the potential energy of molecules is increased, then it means the material or the substance is changing state from one form to another. And when change of state starts, there is no change in the temperature of the material. So last time I gave you a practical situation that when you put water on fire and insert a thermometer into the water, as the water is heated, you realize that there is increase in temperature. The thermometer reading will be rising, or the mercury level will be rising to indicate that, yes, temperature is increasing. Then when it gets to 100 degrees Celsius, when it rises to 100 degrees Celsius, the thermometer reading will not change again, because 100 degrees Celsius is the boiling point of water. And this is the temperature where water changes from liquid to gas. And so it will not change again until every water or liquid has turned to gas. But then you have nothing in the container, and so you wouldn't even see anything. So every change of state occurs at a particular temperature, and that is the boiling point, melting point, freezing point, and occurs at a constant temperature. Okay, so last time I also told you that if you take vapor and boiled water, vapor is more dangerous with regards to the burns meted out to people than boiled water. This is because, you see, before water changes to vapor, it must absorb heat energy to take it from maybe a temperature of 0 to 100. At 100, water begins to boil, boiling point. At 100, we are still constantly supplying heat. This constant supply of heat at 100 will not show up in the temperature, but it will work in the intermolecular bonds of water. And when there is increase in intermolecular bonds, change of state starts. So the excess heat energy that is supplied goes to work on the intermolecular bonds. Okay, so that is why vapor has excess heat energy than water at 100 degrees Celsius. And this explains the reason why burns from vapor is more dangerous than burns from water, boiled water at 100 degrees Celsius. Please, is that okay? All right. So that is it. Now, for change of state, there must be a certain amount of heat energy that must be absorbed. This heat, the heat energy required to change state is known as latent heat. Latent heat. So latent heat is any heat energy that changes the state of substances or materials. And then sensible heat. Sensible heat is responsible for change in temperature. So latent heat, change of states, then sensible heat, change in temperature. So it means vapor has both latent heat and sensible heat. But water, boiled water at 100 only has latent heat. And this is the reason why vapor is more injurious than boiled water. So the amount of heat that must be absorbed to change the state of a material or a substance, okay, at constant temperature is known as either latent heat of fusion or latent heat of vaporization. Now, let's take to one of them. When we have solid changing to liquid. Solid changing to liquid, this is termed as melting. So melting is a process whereby solid changes state to liquid. Technically, this is also known as fusion. Technically, melting is also known as fusion. So the amount of heat energy that must be absorbed by a material to change state from solid to liquid, okay, at the melting point of the material at constant temperature is known as latent heat of fusion. So latent heat of fusion refers to the amount of heat energy that must be absorbed or liberated to change states from solid to liquid or vice versa at constant temperature. Okay, so when we talk about latent heat of fusion, this is it. That amount of heat energy that must be absorbed or liberated. Absorbed or liberated because from solid to liquid, substance must absorb, as said by you. Okay, then from liquid to solid, that is freezing. Liquid to solid, heat energy must be given out, liberated, okay, to change state. That amount of heat energy responsible for fusion, that same amount of heat energy is also required for freezing or for solidification. Okay. So this is the reason why I'm using absorbed or liberated. So for pure crystalline materials, the same amount of heat must be absorbed or liberated in order to change from solid to liquid or liquid to solid in that manner. Then, because different materials have different or require different amounts of heat to change states, we look at 1 kilogram mass of a material, just as we saw in specific heat capacity. Different materials have different or require different amounts of heat energy to raise their temperature. Here too, different materials will require, different solids will require different amounts of heat to change state from solid to liquid. And so we look at, we don't look at the general mass of material, but we look at 1 kilogram mass of a material, and then the quantity of heat energy that is required to change state from solid to liquid. So we also talk about specific latent heat of fusion. Specific latent heat of fusion given by the symbol capital L subscript F. Now we define the specific latent heat of fusion as the quantity of heat energy that must be absorbed or liberated, okay, for 1 kilogram mass of a material or solid to or of a substance or material to change states from solid to liquid at its constant temperature. Please let me take a call quickly and get back to you. Okay, so that is it with specific latent heat of fusion. So the amount of that quantity of heat energy that must be absorbed or liberated, okay, by 1 kilogram mass of a material at its melting point to change state from solid to liquid at a constant temperature. Please note the definition so well. Now, so if I'm giving X mass of a material to calculate its to calculate the quantity of heat energy that must be absorbed or liberated in order to change states, then that quantity of heat energy, KOF, substrate F to denote that it is fusion, would be equal to the X mass of the material times. Now, because we know the amount of heat energy that is required for 1 kilogram mass, that is a constant value. If you give me X mass, it's just a matter of multiplying X by that known 1 kilogram heat, specific heat capacity that is known, and I'll be able to determine the total thermal or heat energy required. So this is times X times LF. Don't forget, here change of temperature does not come in because change of state occurs at a constant temperature. So generally, QF, which is that quantity of heat energy that must be absorbed or liberated, is equal to any mass M times L substrate F. This is the formula for calculating that total amount of heat energy required to change state from solid to liquid. Okay, so please note that for change of state, change of temperature does not come in. LF therefore is equal to Q over M. I want somebody to help me determine the SI unit of specific latent heat of fusion. Lizzie, Asumani, help me determine the SI unit of specific latent heat of fusion, LF. Or they are not here.
Said yeah, please. Joule per kilogram.
So quantity of heat energy in joule, and then M is in kilogram. So the SI unit for latent heat of fusion is joule per kilogram. Okay. Joule per kilogram. Then let's also look at changing state from liquid to gaseous.
Yeah.
Hello, Epia.
Please, can you write the definition of specific latent heat of?
Okay, let me, I said it, but I thought you were writing it. Okay, so specific latent heat of fusion is that quantity of heat energy the quantity of heat energy that must be absorbed or liberated. That must be absorbed or liberated for 1 kilogram mass. For 1 kilogram mass of a material to change state. For 1 kilogram mass of a material to change state from solid to liquid at its boiling point, from solid to liquid at its melting rather, sorry, at its melting point at a constant temperature. The quantity of heat energy that must be absorbed or liberated for 1 kilogram mass of a material or substance to change state from solid to liquid at its melting point at a constant temperature. Now I said, hello, Amma.
Please, isn't the melting point the constant temp?
You see, change of state starts at a particular temperature, and this is the melting point. So you need to talk about that temperature which begins change of state, and also need to talk about the fact that when it starts, it occurs, that temperature or does not change or is constant. Is that okay?
Okay. Yes.
So that same amount of heat energy must be released when the substance is changing from liquid to solid. So when it's from solid to liquid, that heat energy must be absorbed. When it is changing from liquid to solid, that quantity of heat energy must be given out or liberated. So when it is here, it gives out, it absorbs the same energy. When it is the other way around, it releases the same amount of heat energy. Okay. I want to give you figures. One. Okay, so for example, the specific latent heat of fusion of ice. Please put this note down. The specific latent heat of fusion of ice is 335 kilojoules per kilogram. 335 kilojoules per kilogram. Okay, the specific latent heat of fusion of ice is 335 kilojoules per kilogram. Please, can somebody tell us what this statement means? What it meant by the statement that the specific latent heat of fusion of ice is 335 kilojoules per kilogram. What does it mean? A volunteer to volunteer, else I'll call somebody. What does it mean by the statement that the specific latent heat of fusion of ice is 335 kilojoules per kilogram? What does it mean? Alvina. Alvina, over to you. Share your view or your views with us. Now, Kirsten, you are also here. LF of ice is 335 kilojoules per kilogram. What does it mean? Charlotte. Lizzie. Charlotte, tell me what you think.
It means that the quantity of heat that must be absorbed or liberated for the ice to change from solid to liquid is 335 kilojoules per kilogram at a constant temperature.
Anyway, Charlotte has given us her take. Thank you, Charlotte. Lizzie, let me hear from you. Lizzie?
So I also say that the amount of heat that must be absorbed for ice. So from ice to change from solid to liquid at constant temperature is 335.
Okay, let me hear from the gentleman. Oh, Kelvin, you're also here. Kelvin. Kelvin.
It means,
what is your view?
It means that 365 kilojoules per kilogram is the amount of heat ice has to absorb in order to change its state.
Okay, listen to my take. It means that the amount of heat energy that must be absorbed. Let's even talk about absorbed, okay, and leave the liberated for a while. The amount of heat energy that must be absorbed by 1 kilogram mass of ice. So I've talked about the unit mass. That must be absorbed by 1 kilogram mass of ice at 0 degrees Celsius. Here, I've also talked about its melting point at 0 degrees Celsius to change state from solid to liquid at constant temperature must be 335 kilojoules. Okay, so let me put the statement now. The statement means that 335 kilojoules of heat energy must be absorbed by 1 kilogram mass of ice at 0 degrees Celsius. Yes, Odile.
So please, does that mean that ice melts at 0 degrees Celsius?
Yes. You see, water freezes at 0. Okay, liquid to solid, 0. Okay. And so solid, liquid to solid, 0. solid to liquid, 0. So when you are freezing, the moment it gets to 0 degrees, it starts. When it is melting, okay, the moment it gets to 0 degrees, it also starts. For pure crystalline substances, that is materials without any impurity. So the statement, I've forgotten the statement. The statement means that 335 kilojoules of heat energy must be absorbed by 1 kilogram mass of ice at 0 degrees Celsius to change states from solid to liquid at constant temperature. That is what the statement means. Please, is there any other question? And that quantity of heat energy is given by the mass times the magnitude of 1. So the mass times 1 kilogram, the amount of heat required by 1 kilogram mass gives the quantity of heat energy. So where Q equals quantity of heat energy, absorbed or liberated, M mass of substance, then LF specific latent heat of fusion. And this is usually a constant. So once it's constant for any 1 kilogram mass, if you are given M mass, you can always calculate to determine the amount of heat energy required to be absorbed or released. Please, is that clear? Any question? Yes, it's unfortunate time is up. We couldn't finish vaporization. And then look at the cooling curve. Heating curve and then the cooling curve. We'll do that on Monday. Okay. Please, I'll forward questions to the group. If the question comes and you have issues, contact me. Do not sit down, okay? Don't think, oh, it's difficult, blah, blah, blah. Contact me and we'll do it together. Okay, so may the good Lord be with you. This is where we'll end today's session. In fact, so we meet again on Monday. May you be protected and favored. Until then, bye-bye.